Here I'm going to be looking at probability, going through a set of notes, trying to give you a better understanding of how to calculate the probability of certain events happening. Now, this is denoted by PE here, the probability of an event happening. Now, that's going to be the total number of successful outcomes in the event over the total number of possible outcomes. So, for example, let's say you're rolling a die and you wanted to find out what would the probability of rolling a 3. Well, the number of successful outcomes there is just 1 because there's only one 3 on the die. Now, the number of possible outcomes is 6. So the probability of rolling a 3 is going to be 1 over 6, 1/6. And that's usually how we leave our probabilities, as fractions. So we could just say the probability of rolling a 3 is equal to 1/6. There's a range of probabilities going from 0, which is just impossible, it cannot happen, up to 1. So the maximum value of a probability is going to be 1. It's certain to happen. Now, something that is also quite useful is what's the probability of the event not occurring? The probability of the event not occurring is 1 minus the probability of the event occurring. So if we were to look at the question above, what's the probability of not rolling a 3? Well, we look at all the other chances, which is going to be 1 minus the probability of throwing a 3, which is 1 minus 1/6, which is 5/6. So let's say there were a certain number of discs in the bag. Let's say there were 10 discs in the bag. 5 of those discs were blue. What is the probability of pulling out a blue disc? The probability is going to be 5 over 10, which is a half or 0.5. Now, what happens when we have two events? When we have two events, what you could do is just write out all of the possibilities for both events, and that is called creating a sample space. Okay, so we might want to create a sample space, which is a set of possible outcomes in a list or a table format. So let's say for this one you wanted to know, so you're rolling 2 dice and you wanted to find what is the probability when you roll 2 dice that the two numbers together added up to a 7. So you might want to create a sample space. So I'm just going to show you that now. So this is a sample space. If you rolled 2 dice and you were asked what is the probability of getting the total score equal to 7, what you would do is you'd write out one set of outcomes on the top, one set of outcomes down the bottom, there, one set across the top. If you rolled a 1 and then another 1, the total sum there would be 2. If you rolled a 2 and a 1, the total sum would be 3, etc. So if you wanted to see what was the probability of obtaining a total of 7 when you roll 2 dice, well, you write out the probabilities, and what we can see is there's 6. So the probability of getting a sum equal to 7 is going to be the total number of successful outcomes, which is 6, which I've highlighted in yellow, over the total number of outcomes, which is 36. So that gives me an answer of 1/6. Okay? So that's an idea of a sample space, where you write out all the possible scenarios for the two events. So the next thing we're looking at now is relative frequency. Now, this is to do with kind of experimental probability. We know that not all events are equally likely, so we kind of need an estimation based on previous results to try and characterize a form. Now, we know that the probability of, if you flip a coin, the probability of getting ahead is 1 and 2. Okay, because the successful outcomes is 1 and total number of outcomes is 2, so it's 1 and 2. Now, if you flip a coin 10 times, the chances are you might get 6 heads out of 10, you might get 8 out of 10. Okay, so in general, what's going to happen there is, as the number of trials increase, the relative frequency gets closer and closer to the theoretical probability. So if I'm flipping a coin, I know that the theoretical probability of getting ahead is 1 in 2. But that's not going to happen every time. But if you flipped a coin 100 times, more and more likely the probability will be closer and closer to the actual theoretical probability, which is 1 in 2. So you might get 52 out of 100, you might get 48 out of 100, but that would be better approximation than 6 in 10. So with relative frequency, it's using experimental probability. So carrying out trials to try and find out how likely an event is to happen. And so what we have is a situation where the probability of the next event happening is the relative frequency of that event. So let's say you're talking about form in football championship, and you talk about a team that has won 6 of the last 10 matches. So the relative frequency there would be the 6 wins out of a total number of 10 matches. So the probability of the next event happening is the 6 out of 10, which is 0.6, or 3/5. Something which I haven't mentioned here is expected frequency, which I'll talk about now. And expected frequency is the probability times the number of trials. So for expected frequency, all we need to do is work out what the probability of the event happening is times the number of trials. So for example, let's say we're talking about a lotto draw and the probability of winning this lotto is 1 in 50. Let's say the lotto was carried out 1,000 times. The expected frequency, i.e. the number of wins, would be 1,000 times 1 over 50, which is 20. So we'd expect 20 wins there. That's expected frequency. Another thing is called expected value. So expected value is used for things like working out whether it's worthwhile carrying out a draw or something like that, or a lotto. Let's say the probability of winning something is 1 in 10, and the winner gets €2,000. Well, the expected value that you're going to be paying out there is €200. So depending on the number of entrance fees and the other number of prizes and the probability for those prizes times its value, you would determine whether it's worth carrying out the draw or not, i.e. whether someone's going to make a loss or a profit. Just remember that expected value is a probability times the actual value. And I'll be going through a past paper like that on another video. So now what I'm going to start to talk about is multiple events, and talk about mutually exclusive events and non-mutually exclusive events. So there are a couple of rules that we need to remember. The first rule I'm going to look at is called the addition rule. What that means is if you've got 2 events and you want to know what the probability of one event or the other event happening, then all you need to do is add the 2 probabilities together. That is the case for mutually exclusive events. That is, the events cannot occur at the same time. So for example, if I'm looking at a mutually exclusive event, you could think about a pack of cards. There's 52 cards in a pack. So let's look at this situation. Let's look at the probability of, from a pack of cards, of drawing a queen or a king. The probability of drawing a queen from a pack of cards is equal to 4 over 52. And the probability of drawing a king is equal to 4 over 52. Because you can't get a king and a queen on one card, that total probability is going to be 8 over 52, which is just equal to 2 over 13 in its simplest form. So you can see why they're mutually exclusive there. You can't, when you've got 2 events of the same experiment happening, you can't get a queen or a king at the same time, so they're mutually exclusive. So the probability of one or the other happening is just the probability of the first one happening plus the probability of the second one happening. Now, this will change if the 2 events are not mutually exclusive. So for example, if the 2 events can occur at the same time, so let's say in this one you're looking for the probability of a queen or a heart when you're picking a card from a deck of cards. Now, that's going to be the probability of getting a queen, which is 4 over 52, plus the probability of getting a heart, which is, well, there's 13 hearts, so that's 13 over 52. But here we have to subtract the probability of getting a queen and a heart, i.e. the queen of hearts. Well, there's 1 queen of hearts in the pack, so what we need to do is subtract the 1 out of 52. If we don't do that, then we're going to be counting it twice. So the answer to that then will be 16 out of 52, which is 4 out of 13. So another thing to keep in mind here is set notation. The probability of A and B occurring is probability A intersection B. Probability of A or B is A union B, highlighted in green, and the probability of A and B is the probability of A intersection B, if you remember from previous maths. So the next rule is called the multiplication rule. This is really important for determining independent events. Independent events are events that can happen at the same time or happen one after the other. It's just that they don't impact each other. So if you have an independent event then the probability of A and the probability of B, provided that A has no impact on B and B has no impact on A, then that probability of A and B happening is the probability of A times the probability of B. For example, if you were to roll 2 dice, and what is the probability of getting a 6 followed by a 6? Well, the probability of getting the first 6 is 1 over 6, and the probability of getting the second 6 is 1 over 6. So the total probability there is 1 in 36. Now, the second throw does not in any way impact the first. There's no conditional probability, which I'll talk about next. So the probability of A definitely happening, followed by the probability of B definitely happening, is 1 over 6 times 1 over 6, which is 1 over 36. So that is the multiplication rule for independent events. Okay, so really important there for that multiplication rule that the events themselves are completely independent. Just to remind ourselves, 2 events are independent if the occurrence or non-occurrence of one doesn't influence the probability of another thing. So if there's any influence whatsoever, then it's not independent. What we're going to look at next is something called conditional probability. And conditional probability is the probability of one event happening given that the other has to have happened. So definitely not independent here. So conditional probability we're talking about next. So conditional probability is given by this notation here with a single line just like this. And this is the probability of A happening given that B has already occurred. So if you've got your 2 events A and B, and we know that B's already happened, that might influence the probability of A happening.